Welcome everyone to the afternoon session of the Einstein Toolkit meeting. Our next speaker is Steve Brandt. First of all, thank you very much, Steve, for setting up the tutorial server and checking everything in advance. And thank you also for giving both tutorial and talk. Steve is a professor of computer science at the Louisiana State University and the assistant director of the computational science at the Center of Computation and Technology at LSU. He is also a maintainer of the Einstein Toolkit. His work includes parallel programming, parallel languages and its tools, science getaways, and high-performance computing. And he will be talking about introduction to Einstein Toolkit. Steve, we can take it from there.
Yes, I just realized I have the wrong slides showing.
Yeah, 2021. Yeah.
Yes. Hold on.
Yeah.
You can restart this. Okay, so this is the traditional Einstein Toolkit talk that we give for new students and people who are new to the project every year. The Einstein Toolkit is a collection of scientific software components and tools for general relativistic astrophysics that was started in 1997 at the AEI. It's freely available as open source at this URL. It's been supported. It's been supported by. Oh, by the way, can you see my pointer?
Yes, I can see it.
All right, good. It's been supported by these NSF grants, but obviously a lot more. I think it's had continuous NSF support for most of its life. It is a set of state-of-the-art tools for numerical relativity. As we said, it's open source. There are currently 465 members from 326 groups and 49 countries. Membership means that you've gone to our webpage and you've signed up as a member. And that means, you can get email if you want from the users list. But that's all it means. I mean, it's not like there's dues or anything of that nature. And if you want to look at that list, you can go there and members, there you go. And you can see all the people who have signed up. And you can give a link to your webpage if you want and get your university mentioned in lights on the Einstein Toolkit website. We have over 481 publications and 58 theses as of June 2024. I did not attempt to update that number, but I'm sure it's grown by a couple. It has been a spec benchmark twice. We're well on our way to becoming a third one. We've gotten money from the spec people for that, and hopefully it will complete soon, but it's a very long process. Einstein Toolkit received a Gordon Bell, well, it was technically called just Cactus back then. It was a Gordon Bell Prize in 2001 and a Sidney Fernbach Award in 2006, which is quite a big deal, actually. It has appeared in one science fiction story, Black Taurus Run, which is available on New Myths, which is an online magazine written by me. And at some point, there will be a science fiction novel which mentions it. So, stay tuned. The Einstein Toolkit is regularly tested on a variety of hardware platforms. It has user support through various channels, and below you see the people who have volunteered to be maintainers, and to put their name on the line for making sure that the toolkit continues to run reliably. These pictures are possibly a little dated, but you can still recognize us all. The science, there's a lot of different science that is enabled by the Einstein Toolkit. There's black hole mergers, of course, which is what started the whole thing. That was the goal from the beginning. But there are also neutron star mergers, supernovae, accretion disks, boson stars. You can, probing various forms of alternative gravity and hairy black holes and cosmic censorship hypotheses, all kinds of anything related to general relativity is potentially available for the Einstein Toolkit to do. Our current release is the Martin D. Kruskal release, It's the 30th release. It came out in May. The release managers were Maxwell Rizzo and Roland Haas. The release comes with a Slurm-based multi-node tutorial that we're going to be using later today, which, I had to struggle to get ready during Thanksgiving week here. The Einstein Toolkit has many new features from the previous release. It has a CCE export for Spectre Cauchy characteristic evolution. It's got an FLRW solver. It's got derivs for 6th and 8th order finite differencing, Carpet X, which is our new driver thorn for the Einstein Toolkit. More on what a driver thorn means later, but Carpet X makes it possible for Cactus to use GPUs, which is an important piece of functionality since these days, if you can't use a GPU, you're probably using 1/1000th of the machine. There is a new gallery example for a black hole hair in axidilaton gravity. Okay, so solving big problems like this is a community effort. Why? Well, because first there are computational challenges and hardware changes. So we started with something like this long ago, and then eventually we got to things that look more like this. And then we got a machine like this, which is the first exascale machine recognized on the top 500 lists. There were probably others that weren't recognized. This is Frontier, and this is El Capitan, which is the current top 500 machine. And it's got a nice, pretty picture on its side. So the point is with the Einstein Toolkit is these are big problems. They need big machines and big resources, and you need the computational support from the toolkit to be able to use them. Not everybody should, when they set out to write their PhD, have to re-implement all that stuff from scratch. So you want to make use of cutting edge science. You want to use the latest numerical methods. You want to make use of the latest hardware. And, that's cache. It turns out when I was a graduate student, machines didn't have cache. That wasn't something you worried about. You did have vectors, but, and that was the only thing you had to worry about. If you could make your loops vectorized, you won. You'd solved performance. But now there are also accelerators, which are also kind of like vectors. You need to scale to many cores because, we now have parallelism. Not that that's new to any of you. We also have to be able to scale to many nodes. You need to have the right algorithms. So when you're looking at performance, algorithms are at least as important as having fast hardware, probably more so. And over time, better algorithms tend to come around and help you speed things up, more. And so efficient use of all that hardware is a complex and tedious thing, and it requires experts from different disciplines, and it requires good data layouts. And so to ensure correctness, you need good modularization on a number of levels and understanding of advanced programming concepts. And the design needs to be, and implementation needs to be carefully thought out in order to ensure extensibility and portability. And not every single person who wants to do numerical relativity needs to go through all that, right? That's the point of having it a community effort. We can have computer science, computer engineers, physicists, and so on all come together to make things work. Now, at a high level, when you have a distributed code running, what you need to do is you need to chop up your grid. You need to put a little piece of space-time on each of the computational nodes. And the way you do that is with a technique called ghost zones. Now here we have just one ghost zone, but in a real simulation, you might have 3 or so for each thing. And the idea is each processor has a domain that encompasses these inner nodes. And this node actually matches something on the other machine. And what happens is we copy from these inner nodes to these outer nodes like this between every update of the grid. And by doing this, by just copying these ghost zones and updating the middle part, we're able to carry a computation forward on multiple processes. Now, if you haven't seen this before, this may be a little confusing. I just want to stop here and ask if anyone has any questions. Just speak up if you do. All right.
I don't see any questions here.
All right. So now I showed that to you in 1D, but of course you want to do this in 3D. And well, here's 2D, right? Which showing you kind of the same thing. We're showing the overlap and then the ghost zones. And then of course you have sort of zones that you don't modify on the outside. These are called your boundary zones. And they're a similar but different concern. And your grids might not all be boxes, right? Or they'll all be logical boxes, but they might not actually be literal boxes. So here is the kind of thing that you typically want to evolve, right? You want to have a nice spherical outer boundary so your waves can propagate well. But on the inside, you need to resolve things in more detail, and you need, usually people want to have some kind of Cartesian mesh where you refine around the black holes or neutron stars or whatever you have. So as far as what the programmer knows, each of these boxes is logically a rectangle, and they're just doing updates with with traditional loops. But the coordinate systems for each of those boxes are slightly warped, and so that's kind of the way. This is kind of the picture what people do when they want to evolve. The other nice thing about having these patches the way they are, you notice that we don't just have one spherical patch. The idea is we want to avoid having the axis on the grid. The reason you want to do that is because it tends to be problematic, right? The size of the grid of the elements becomes very small near the poles, and that tends to lead to very small Courant conditions. So you're stuck with either very tiny time steps or just avoiding them altogether. And so this avoids them altogether. So back at looking at the computational challenges, we have various ways of addressing the things you saw before. So we have vector machines, and for those we have tools like Crank and NURPy, which automatically generate code. And these can put in the vector intrinsics. The problem, of course, is that the Einstein equations, because they're hundreds of terms long, most of the compilers aren't able to vectorize them. They just see the length of the expression and they give up. So we have tools to manually insert those things, which it turns out is not a trivial operation at all, even if you understand the equations as a human better than the compiler. Scaling to many cores, typically we use OpenMP for this task, and that's fairly straightforward. Scaling to many nodes is of course much more work, and for that we need MPI at the lowest layer, and Carpet and Carpet X, our two driver thorns, will make use of MPI. Adaptive mesh refinement is provided to us through Carpet, Carpet X, method of lines. These are names of modules within the Cactus framework. It also these days makes use of a software project called AMREX, AMREX, for Adaptive Mesh Refinement for Exascale. It's a project that was funded by the DOE. I'm not sure who currently funds it, but it's the foundation on which Carpet X is built, and it is the thing that gives us access to GPUs. Which is, as I say, if you want to use GPUs, you have to use Carpet X with the Einstein Toolkit. Machine learning, we don't have anything for that, but it's the next big thing. Somebody's got to do it at some point. I think Roland has a paper where he is involved in a paper, at least, in which they use machine learning for hydro. FPGAs, as far as I know, nobody has ever put the Einstein Toolkit on an FPGA in any way. Field programmable gate array. It is another tool for accelerating computation. An ASIC is a custom chip that you could make. Imagine a chip designed to run Cactus. That could be pretty interesting if it ever existed, and maybe someday it will. Neuromorphic processor, which is just a different kind of hardware, especially designed for machine learning that resembles a human brain. Qubits. Quantum computing is coming. Can we do anything with it? These are just sort of items of fear that I have. Someday I imagine somebody handing me a board that's got, a neuromorphic processor, a couple of qubits, a GPU, an FPGA, and saying, make use of this whole thing. I don't know what the future hardware is going to be, but the idea is we want to be able to make use of it, whatever it is. Okay, so those are the big important challenges, right? You've absolutely got to understand your hardware and get it right. But there are also more mundane challenges. Efficient I/O. Efficient I/O is a huge problem. Seymour Cray said that he said the definition of a supercomputer is it as a device which turns a compute-bound problem into an I/O-bound problem. And the point is, right, whenever you try to write out your results from your simulation, it winds up that it can easily wind up that this is the slowest part of your whole thing. And with our current situation, we're still struggling with this issue. I mean, you can get efficient I/O during the simulation, but maybe it takes forever to load it and visualize it. And if you can't visualize it, you've just got bits. So HDF5 is a common file form portable binary format, which has served the Einstein Toolkit well for many decades, but maybe it's time for something new. Adios 2 is a backend. You need the ability to checkpoint and restart. Whenever you're running a huge simulation, whenever you have a big science code, this capability is a must, because your simulation might take a month to run. And your big machines, the big clusters that you want to run on, are not going to let you run for a month. And there's good reasons for them. They're not just being mean to you, right? I mean, the point is nodes fail for various reasons. And the longer they run, the higher the chance of failure. And imagine that you have a 30-day simulation that you've ran. On a day 29, it crashes and you lose all your data and you have to start over. This is just not acceptable, right? You can't do science this way. You'd never get a simulation done, no matter how efficient your code was. If you can't checkpoint and restart it, it's useless. So you've got to have that built into your framework. You have to have the ability to checkpoint and restart, or otherwise you're dead before you start. And again, these are all sorts of things that not every programmer should have to worry about. This should be something that you should be able to take from someone else and leverage, and not have to fight that same battle over and over. Parameter parsing is much more minor, but it's a thing that needs to be done, right? There needs to be a standard way of communicating parameters to your simulations. And for something like the Einstein Toolkit, there's going to be hundreds, if not thousands, of parameters to look at and set and make sense out of. Visualization is another important concern, right? If you can't visualize your data, you'll probably never understand it, and it will probably remain useless to you. And the Einstein Toolkit has tools for that. It could probably still use work if somebody's looking for a computer science test to do. There's probably some work to be done there. Analysis. So you need standard tools for event horizon finding and wave extraction. And again, you don't want to write all these yourself. At one point, it was a big deal to try to steer computations interactively while they were running. And the Einstein Toolkit has a tool for that. And the Einstein Toolkit has tools for that, and they haven't been used in many years, but they're there. And then there are collaborative challenges, right? So these are two typical black hole researchers here that you see trying to meet and discuss what to do. And they have a common problem, right? We want to be able to solve general relativistic physics and do things with it. And we have multiple groups that want to work on this problem. I mean, they could all just do their own thing, of course, and re-implement everything themselves, but that's not necessarily the most efficient way to do things. And they all want to make use of the same computational hardware, right? I mean, the big machines, not everybody can have them. At one time, LSU was able to have the top 40 machine on the top 500 list, but nowadays the competition has gotten so stiff that we can't even get on the top 500 list. It's just gotten too outrageous. And so we need to form a community of some sorts. And we do that, with a number of different meetings. We have calls, which are actually Zoom, but and we have web pages, and we have chat capabilities, and we have email, and we make use of all these tools to connect our community. And we also make use of other tools like Git and, not all these things that are here are still used, right? But we use Git. We don't use Mercurial anymore. We did at one time. At one time, we used all the different source code managers. Git has taken over the world, however. And let's see. We have a wiki that we use to encode our wisdom for doing releases and other processes. We have workshops like this one. And anyway, we have common problems that we all want to work on. And we have competition, right? Each group wants to publish papers. They want to get their research out. They want to distinguish themselves. And so we've got this problem, right? We want to work together, but we want to do our own thing and not share. So we want to share and we want to not share. And the way we've done this with the Einstein Toolkit and Cactus is we've made the tool open source, and anybody can make use of it to publish papers and do their own research. They don't have to make everybody who was there an author. We do ask that they cite the toolkit so that people can get some kind of credit, but we don't require it, right? I mean, we say we would really like you to cite us, and I think it's just good manners. But that's the way we've done it. And typically, the way this competition versus cooperation problem has been solved is that people develop their thorns, they do their science, they publish their papers. When their papers are published, they put the thorn back into the toolkit, and other people can use it to publish their papers and maybe cite the original work. And so this is how we've solved that competition cooperation problem with the Einstein Toolkit. Another important thing is standards, right? And it doesn't mean just external standards. We have to have standard ways of writing code and of doing things in order to enable all our different modules that we write to work together. And the Einstein Toolkit has been quite successful. I mean, sure, the toolkit has shown its age, and has become a little crusty since 1997. But the standards that it was built on, the standards that it established, have enabled cooperation over all that time. So that's sort of the essence of its success to date. And of course, we always use this to measure in the Einstein Toolkit. In the Einstein Toolkit, we have a standard set of units, which are a solar mass, and C equal G equal 1. And that works out to be about 5 microseconds for the time scale and about 1.5 kilometers for the distance scale. And, as an exercise, you can compute your age and mass and height in terms of those units. We use standard data formats. Okay, and we have tools that are built around the whole thing and standard tools that we use. So a lot of this framework is built in Perl. I guess if it was built today, it would be Python, but Perl was the cool kid on the block at the time. And Fortran is not well supported by CarpetX, but it's still supported by Carpet. Who knows? Maybe we'll have other languages involved in the future. We can work on various platforms like Linux and Mac and Windows. Windows, the only way I've really gotten it to work is through WSL, which is sort of a Linux environment on Windows. And so we have ways of getting credit to and from the various groups, as I've described. And so the collaboration currently spans researchers in the USA and in other countries. And you can see this is a fairly long list of places. And depending on the year, some of these places may be more active in supporting the Einstein Toolkit than others. But as you can see, it's got quite a span across the globe of interconnection. And it looks like I'm way ahead of time for whatever reason, but whatever. Okay, so the goals of the Einstein Toolkit, we want to be community driven. We want to have core computational tool. We want to provide a core computational tool for numerical astrophysics. And we also want it to be a general purpose tool. The Einstein Toolkit has been used to do non-relativistic applications over the years. There was I was involved in a shallow water equation solver that was used on it for a while. There have been black oil and disease simulations as well. I mean, they haven't stuck around the way the numerical relativity applications have, but they are possible, and it might be useful to use them for other things in the future. We have various components. So Cactus itself, the core part, which is the flesh, which is just a little bit of glue. It's barely anything. It's just a standard way for all the different tools to talk to each other. We've got SimFactory, which is a tool for running and building Cactus applications. We've got Crank and NURPy for generating code. Crank is based on Mathematica, and NURPy is based on Python. We've got a whole library of science modules growing all the time and takes insanely long to build from scratch because it's so large. But you can pick and choose your science modules, and we'll show you how to do that later on. We have guiding principles that we're open. We're going to be open source. We're gonna not hide anything. We're not going to make anything secret. I mean, not anything that's officially part of the toolkit anyway. But you can have things that are secret and private that leverage the toolkit that you keep for yourself. We want to be community driven. We don't want to just be we don't want to just be an empire that runs out of one place. We try to maintain good interfaces. We want to have separation of physics from computational infrastructure. This is one of the things, as I said, that I think we've done well over the years. Anytime I look at a piece of science code that isn't the Einstein Toolkit, I typically see the time integration method, like the Runge-Kutta, is deeply embedded in the code. It's not easy to just switch it out for something else. It's like tied to the actual system. And there's, inside their main time evolution loop, there's usually an if statement to print something or write something to disk. And so all these different concerns get represented often in the same source file in most tools I've seen that weren't the Einstein Toolkit. And this, of course, makes your code very brittle and fragile and hard to update and hard for other people to use. But if we keep the different concerns separated, as the Einstein Toolkit has managed to do, you can build a code that can continue to be used for decades. The code is production ready. I won't say our documentation is perfect, but again, I would say it's better than most of the codes out there, and we do work at it. It is a high quality code. We test it rigorously and often. I have this thing that I tell my students when I teach a computer science course: if you don't test your code, it doesn't work. I mean, no matter how good you think it is, it absolutely will not work if you don't test it. So Cactus started when it did start was in 1997, as I said, and it just had a few little small components. And over time, with support from our administration and grants, we're able to grow it and continue to grow it over time. And most modules are open source, but not necessarily all. And we have a base set of modules that are based around this equation here that we all know and love. So we have the space-time curvature. We have some constants. We have matter terms. And inside the matter terms, we break that up into hydrodynamics, electromagnetism, scalar fields, and particle radiation. And to represent these, we have various thorns. So we have ADM base and T mu nu base. And these are mostly just a set of standard grid functions, right? So if you want to be able to make use of space-time for some reason, You need GXX, GYY, and so on. And Team U base, right? You have their standard hydro quantities in the standard way you represent them. And MLBSSN is not going to use the ADM equations as such, right? Because we know the ADM equations, as they were originally written, are not well posed. They're not stable. When I was a graduate student, we were constantly trying to fight to get black hole evolutions to work at all because of that. But MLBSSN formulates them in a different way and is able to get them to be well posed and evolve stably. But it still needs to translate back and forth between the ADM quantities because that's sort of a standard interface. Remember, we talked about standards, and all the other tools know how to get at the ADM quantities and manipulate them. So we have the capability of translating to and from the ADM quantities. And so we have other thorns, right? We have the GR hydro thorn, which is going to handle the evolution of the hydro quantities and manage the equation of state and so on. And that's going to make use of Team UNU base and something called hydro base. And so you can see we've got like 3 base modules and 2 higher level modules that make use of them. And the arrows mean make use of. And then you've got initial data and analysis thorns that can make use of them as well. And over time, you can add other things. So there's Illinois GRMHD, for example, and Lean, Baikal, and Praka. And these all make use of these core set of modules, right? So because you've got this core set of standard modules, you can build all kinds of other complicated things on top of it. And all these things are mix and match, essentially. You can use ML BSSN or Lean or Baikal, and you can use GR Hydro or Illinois GRMHD. I don't know that we've tried all the possible combinations of those things to see if there's a problem, but in principle, they can all work because they're all talking to the same standard interface. I've been talking for quite a long time. Are there any questions about anything so far?
You can either raise your hand or type in the chat, but I don't see any questions in the chat either.
All right, all right. So either everybody's asleep or I'm so fascinating and so clear that everybody understands every word I say.
Yeah, definitely.
It's probably that latter thing. Okay, so all right. So as we said, it's open. As we've repeated many times, it's open source, community-driven software development. We try to separate physics from computational infrastructure. We have stable interfaces that allow extensions. We try to simplify usage when possible. In the current world, doing science means running a simulation. And so students need to know a lot about physics, meaningful initial conditions, numerical stability, accuracy, resolution. They need patience and curiosity, and they need to develop a gut feeling for what is right and never to trust their gut feeling. The Einstein Toolkit can't give all that. However, open source codes that are easy to use allow people to work on those things and make progress. So as I say, it's free and open source, no requirement to cite anything. When you do cite it, here is how we request that you cite it. The notion is originally it was a paper like everything else. The standard way of doing things in science has always been, you know, some group of authors get together and they write a paper and they ask for citations forever of that paper. And that model hasn't really gone away entirely, but the problem is when you've got a code like the Einstein Toolkit, you have lots of people who make contributions to it over the years. And if you're just always citing that original paper, none of those people can gain credit. And, you know, you look at something like this as a PhD student is that, yeah, I could spend my time writing infrastructure for the Einstein Toolkit, but who would care? Who would ever know that I did it? Because I'm not on the original paper. I can't, you know, I can't be cited for it. And so what we did, right, was we created this DOI on Zenodo. And every release gets a new DOI with potentially new authors added. If you author anything for the Einstein Toolkit, you get added here and cited forever. I mean, yes, it's a big group of people, but you know, it's kind of like a LIGO comp. It's not as big as LIGO. Let's put it that way. It's a lot of authors, but not as many as on a LIGO paper. And so you can, if you do make a contribution to the Einstein Toolkit, you can get credit and you can put this put, this DOI or a future one on your resume. And so think about that, right? If you wanna be part of this, if you wanna make your mark on the Einstein Toolkit, you will get recognized for it in this and other ways. You can also have papers for the individual components that you write, which is also good. Okay, and we've been saying soon auto-generated list of citations during simulation run. I think we've been saying this for, I don't know, something like 5 years now, and maybe it still is soon, but that's something that we would like to have, right? I think the infrastructure exists for this. Roland, do you remember what state that's in? Maybe Roland is gone for coffee.
Not gone for coffee, but I'm on the bus. Sorry. No, I don't remember.
Okay. Well, we keep wanting to do this, and someday we will, I think. We try to remain cutting edge, and we want to keep that going into the future. So we have, as I say, we had a new driver thorn since the Meitner release, and it hasn't had the full set of things, support built for it, but it's probably going to be, there's probably a lot of this is going to be in the next release. Aster X, which you'll hear about more, and Spacetime X, and new Rad X was in the Landau release. Subcycling for Carpet X is not yet in the infrastructure. Currently, we just do everything with a uniform time step across different resolutions, which turns out not to be as adequate as we had hoped. We've had the Grail thorns from Zach since the Meitner and Landau release. We have a Python code generator, which gives full output of thorns from NERPy. We've got Kerr background support with Self-Force 1D soon. The CCE exporter, which I mentioned earlier, has been in since Kruskal release, and so is the FLRW solver. Every release we have new things, and our next release will be in May. So there's still a chance if you write something new to get into that release. We're currently on a 1-year release cycle. So here's our main website. Visit it often. You can get tools for performing computing and numerical relativity. It's open source. We have a worldwide research community, and it's used in a lot of high-end tech research. And it has been supported by these grants, as we like to always remember to say in all our slides. And that is the end of my talk. Are there any questions?
Thank you very much, Steve, for a very nice talk. Are there any questions? You can raise your hand or type in the chat.